Hello everyone, thank you for being here. I will present you my pyBumpHunter tool, which is a modern-agnostic bumpHunting tool in Python. You can find it on GitHub and also on PyPy, so it's pip installable. So first, a little introduction about the bumpHunter algorithm. So this is a useful algorithm used in the energy physics community that allows to look for an excess or deficit in data distribution with respect to reference background, and also computes the local and global p-value of this localized deviation found in the data. So this bump is done by scanning binary distribution, so it's a histogram-based method. As you see on this picture, you have a background and data histogram. You have a scan window with a variable width that scans over a spectrum and tries to find the interval for which you have the most significant deviation. So this package is inspired by the original BumpHunter algorithm, which is described in this paper. So a little word about local and global. So local p-value tells you that there is a deviation, but it doesn't tell us how likely this observed deviation is to be a statistical fluctuation. So to tell that, BumpHunter generates toys from the reference background and scans them like a normal data. This will give a background-only local p-value distribution. This is what we can see on this plot here. This p-value is turned into a BumpHunter statistic distribution. So we have the pseudo data which correspond to the background-only distribution, and the data which correspond to the observed data. And with that, the global p-value is then defined as the p-value of the local p-values. So why pyBumpHunter? So I decided to make this package because it's allows to have a public implementation based on pure Python. So by pure Python, I mean mostly NumPy SciPy function, and it doesn't depend on vote. So if you want to move away from vote, it's nice. And it was recently integrated into Scikit-HEP, and it's still under active development. So for the features that are currently available, we have scans for 1D and 2D distributions, also signal injection tests in 1D, as well as a sidebar normalization feature. So I will present briefly on this point. So the 1D scan, so this is a basic scan that compares the data to a distribution to reference background. It gives you the position and width of the bump, as well as the local and global p-value. It also gives a root evaluation of the signal content of the bump by computing a data minus reference in the bump window. So for that, what we do is we generate some data. So we have a background histogram, observed data with a little bump, which is localized here, but we can see it like that. And that what we do is that we create a BumpHunter 1D instance. We give it some scan parameters and number of pseudo experiment, binning and range of the histogram, and so on. And then we call the scan function that will do the scan over the data and all the toys. It takes a few seconds to run. There it is. So now we can see the results. So there are 3 plots available. First one is what we call the Torography Plots. This shows the local p-value which is computed for all the intervals that are tested. And here we see that the best interval corresponds to the one that has the lowest p-value. With this interval, we can have a distribution plot with a bump highlighted here, and with a significance map, which shows you the local significance per bins. So we see that the bump corresponds to this excess here, which is located where it was expected to be. And we also have the BumpHunter statistic distribution with the toys in blue and the data in red. So this is for a symbol scan or both signal injection. So this is a bit of an extension of the possibility offered by the 1D scan. In fact, this has the possibility to perform signal injection tests using BumpHunter algorithm to evaluate the sensitivity of a given signal model. So the injection is performed based on the reference background and the data distribution and the signal distribution that you want to test. and the injection stops automatically when you reach sensitivity that you want. Currently, this is only implemented in 1D, but might be extended to 2D. So here I will not run it live because it will take a few minutes, it will be too long. But what we do is that we generate some normal distribution for the signal. We define some injection parameters and we do the scan. So what the algorithm does is it does some background on the scan and then it starts the injection on the first background and do some scans with injection. It goes on until we reach what limit we want, and we get this plot as results. So in order to obtain the error bars, what we do is that we generate some background plus injected signal toys. This will give us a global p-value distribution with a median in the first quartile and the third quartile. This is how we obtain this error bars. So this is for the injection. So now, well, I will answer the question at the end. About the 2D scan, this is an extension of the BumpHunter algorithm to 2D distribution. It works the same way as in 1D. And as far as I know, this is the first implementation of BumpHunter in 2D. So what we do here is exactly the same, but with 2D distribution. So we generate some 2D histograms with some signal which has been injected here. And to treat that, we have a BumpHunter 2D instance, which works the same way as the 1D, but with 2D parameters. And the same way we can call the bump scan method in order to do the scan and generate the toys, and we can plot the results. So there is no torography plots in 2D, but the result obtained here is that I have now my distribution with the bump, which is highlighted. So it's close to where I was expected to be. I also have the local significance map that shows local significance per bin, just like in 1D. And I also have, again, BumpHunter statistic distribution.
Quick mention that this is a 2-minute warning. You a 2-minute warning, and you've got questions coming.
Yeah, I can answer the question now, you mean? So the exact p-value distribution, so local p-value for an interval is based on gamma functions when you, that takes number of events in the data in the background. So I don't have the exact definition here, but you can find it on the paper. And those who want to go away from root, I would not say that moving away from root is necessarily a goal, but it's just that in many workflows we use a lot of Python. For example, if you want to use some machine learning based stuff based on the TensorFlow and so on, you have a workflow which is in Python, and it might be tricky to move back from Python to root and so on. So this way, it's you can simply continue workflow in Python. This is what I meant there. So I don't know if it answers the question. Let's move to the sidebar normalization.
Okay.
So this is
just about ran out of time. So if you could conclude, that'd be great.
Yeah, I will be quick. So sidebar normalization. So this is an option that allows you to automatically rescale the background when you do the scan. So in order to, for example, this example here, you see that there is an offset between the background and data. And background normalization will allow you to compute a normalization scale for each interval which is tested. And this can be done automatically during the scan and can also penalize p-value when there is a discrepancy between data and background outside of the scan window. So here I will not run it, I just show result. I generate this. I create a BumpHunter instance with this option enabled. And when I see the result, I see that it has been rescaled. So since I'm running a bit late on time, maybe I will not present too much the multi-channel combination. This is something which is planned for the next release. I have two combination methods for to combining multiple channels and have a combined p-value, but I will not go in detail to this. So for future plans, for the next release, we have this multi-channel combination, which is planned. Also, future things which are planned are an API refactoring with a data handler class that manage the histogram part separately from the scans. We also add possibility to treat systematic uncertainties and other features as well. For that, your ideas are of course welcome. And the paper presenting the new features in detail is in preparation. That's it from my side.
Great.